Okay, today we're going to talk about risk, and we're interested in risk in the context of fitness. As evolutionary scientists, we're interested in fitness and how fitness is affected by decisions that we make. How does your fitness change if you go from having 2 births to 3? How does your fitness change if you spend 20 minutes in a patch versus 15 minutes? That sort of thing. Fitness is your proportional representation in a population, or alternatively, it's your relative rate of increase in a population. And as a result, these things tend to be nonlinear. Okay, so let's they're nonlinear functions of the outcomes of the decisions that we make. Okay, and so let's put this into something slightly more formal here. I'm going to share my screen. And think about what the consequences for risk are, of risk are for fitness. Where's my screen? There we go. Frozen there for a minute. All right, so fitness. It's going to be an increasing. Well, all right. So it's going to be nonlinear generally. So think about population growth. If the population is growing at some average growth rate R, if you wait to have if you have a birth now, you're 1 over n fraction of the population. If you wait, say, 10 years, you're 1 over n times e to the r times 10, right? The population has grown at this average rate r exponentially since then. So your fitness is going to be a nonlinear function of the timing of your offspring production, the number that you produce, and this is generally true. In a patch situation where you're foraging, right? You're depleting the patch as you eat all the blueberries, right? There are fewer and fewer blueberries. It means that you have to expend more effort per blueberry, right? And so the amount of benefit that you get out of that is actually reduced a little bit as you expend more effort to forage for them, and this is going to have this nonlinear shape. Okay, so it's nonlinear in the inputs, in effort or in returns or whatever it is that this decision is about. Secondly, we expect it to be an increasing function of effort or returns. Right, the more effort you put in, the greater fitness you get out at the end. But we also expect it to be, we'll call it concave, meaning it shows diminishing marginal returns. Okay, and mathematically, what this means is that if our fitness function, let's call it f of x, right, where x is our decision, or is the payoff from our decision, and f is the fitness function. So we want it to be increasing, which means that the first derivative of f is going to be greater than 0, but it's going to show diminishing marginal returns, which means that the second derivative of x is less than 0. Okay, so that's enough to get us started at least. Let's draw a function. Here's a classic, label our axes, x, f of x, label, and draw a classic fitness function that has these two features to it. It is increasing throughout x, right? Increasing x increases f, but it also shows diminishing marginal returns. The increase out here for a unit increase in x is quite a bit smaller than the increase here. Right? Okay, so let's move on from here. What we're going to do is think about this slightly more formally, and think about what. Well, actually, let's go back for a second, and think about you're playing you're taking a gamble, you're taking a bet at some level. We'll call it x bar. So x bar stands for the mean return or the mean effort, whatever the outcome of our decision is. Okay, and you are faced with, for example, a variable output, which means that there's risk, and you can either go up a unit or you can go down a unit. What are the fitness consequences of this gamble? Okay, and for that we're going to do a little bit of analysis here. We have a fitness function. It's generic. We don't really know what explicit form it takes, but we want to get some insight into what risk does for our mean fitness, okay? And risk meaning variability, okay? So what we're going to do is we're going to do a Taylor series expansion of our fitness function. And we're going to do that around the mean return, okay? So X bar. So let's write out our Taylor series expansion. F of X equals F of X bar. Remember, we're doing it around the mean return, plus F prime of X times X minus X bar, right? Plus 1/2 F double prime of X times X minus X bar squared plus, and we're going to stop at the second order Taylor series. Okay, so we've done a generic Taylor series expansion around the mean return, and so now what? The next thing we're going to do is we're going to take expectations of both sides. We're going to calculate the average, right? Because we're interested in mean fitness. So we can write F of X. It's a little clunky looking, but we'll put a bar over it just to remind ourselves that we're talking about mean fitness. And what's the expectation of F of X bar? Well, it's just a single number, right? It's just the function of the mean. And the expectation of a single number is just that single number, okay? So that's easy. The next question is, what is the expectation of this term here, the linear term, the one that just has the first derivative in it from the Taylor series? Well, the mean of X minus X bar, right, is, by the laws of expectation, is 0, because that's the expectation of X, which is X bar, minus the expectation of X bar, and the expectation of a single number is that number. So it's X bar minus X bar, that goes to 0. So there is no linear term in our expectation. Okay, the next term, the X squared term, the second derivative term, what is this value here, the expected value of X minus X bar squared? Well, if you go to your statistics textbook, you will find that this is in fact the definition of variance, okay? The expectation of the squared deviation from the mean is variance, okay? So we can substitute in, we can say 1/2 times F prime of X times the variance of X, okay? And just remember that we're evaluating F of X here at the mean at X bar, okay? And I'll just write down a couple notes here that help us get there, right? So that the expected value of X minus X bar is equal to 0. The expected value of X minus X bar squared is equal to the variance of X, right? And of course, the expected value of F of X bar is equal to F of X bar. All right. So let's just copy this over, make it maybe look a little neater. I ran out of room there. F of X, and I'm not going to write the bar over it. Just remember, this is an approximation, is equal to the fitness of the mean plus 1/2 times the second derivative of the fitness function times the variance of X. All right? What does this tell us? Well, let's remember, we've actually by definition and by biological reality necessity, our second derivative is negative, right? We have diminishing marginal returns. And so what this means is that, and variance by definition is positive, right? It's an expected value of a squared term. So it can be zero, but it can't be less than zero. It's essentially positive if there's any variability at all. Okay, so this has to be positive. This is negative. This means that this whole term is negative. And it means that when there is variance, it drags down the value of the fitness of the mean return. Okay? And what this really shows, so let's just write this out. The fitness function f of x has negative second derivative by assumption and by biological realism, right? And what it really shows us is that variance is generally bad for fitness. Since the second term, 1/2 f prime of x times variance of x is less than 0. It has to be. All right, so that's our first lesson in risk and ultimately in risk management and what it means for real organisms trying to get by in a truly variable world. We'll move on to thinking more about the shape of the function and what that means for how you can manage risk in a later recording.